In this project, we will be finding the ratio between a free-falling and rolling roll of toilet paper so that they both reach the ground at the same time. In order to find the ratio, we first have to derive the necessary equation symbolically. To start off, we use a kinematic equation to find the symbolic time it would take for a single roll to fall, that being the square root of 2 times the height divided by the acceleration. Then we create the equations for both rolls of toilet paper. The first roll is in free fall, so we change the variables to reflect that the height of the first roll is divided by gravity, since acceleration in free fall is equal to gravity. The second roll is not in free fall, as it has an anchor point to provide rotation, so we change the variables to reflect that the height of the second roll is divided by an unknown acceleration. Simplifying the equation, we see that the unknown acceleration divided by gravity times the height 1 is equal to height 2. This on its own isn't very useful, as we don't know the acceleration of the second roll, so we must now find it using the torque equals I alpha equation. In order to find the moment of inertia, it needs to be made clear where the center of rotation is. If the toilet paper roll fully unfolds, it would begin to swing back and forth around the connection point between the line of toilet paper and the roll. Because of this, the center of rotation can be established to be at the roll's outer edge and not at its center of mass. Using this knowledge, we can find that the moment of inertia is the inertia of the roll plus the amount added due to the parallel axis theorem. Finally, we see that the acceleration of the roll, Tp, is equal to the mess of the equation that you see at the end of the second line. The third line begins with finding the value of g over a, because I can't seem to make things simple. However, we can't solve much without the inner and outer radii of the rolls. Using a measuring stick, we establish that the inner radius is equal to about 0.875 inches, while the outer radius is equal to 2.5625 inches. Using these new values, we can see that g over a is equal to 1.558, while a over g, the one we need, is equal to 0.6417. If we were to drop the first roll at a height of 5 feet or 60 inches, the second roll would need to be dropped at a height of roughly 38.5 inches in order to hit the ground at the same time. I also noticed at the end that I didn't symbolically derive the ratio between H1 and H2, so what is at the bottom right is insurance, or past me is forgetfulness. We will be using heights of 60 and 38.5 inches respectively, so that both rolls will hit the ground at the same time. We found these values using the equations you saw in the previous part. Without any further ado, let's test the accuracy of our numbers. As you can see, we correctly calculated the ratios of the heights between the two rolls. It just goes to show you that with the math and a little bit of patience, any answer can be solved. What we have to do now is figure out what to do with all this toilet paper.
I think I know.
What? Ah!